Hi, my name is Thilo and it's my pleasure to present to you the paper Engineering Mesoscale Structures with Distinct Dynamical Implications, which I co-authored with Johannes Höfener and Thilo. The central task in studying complex systems is to explain emergent macroscopic properties from the interactions of the microscopic constituents. Consider, for example, our brain. It would be most fascinating to understand how our ability to process and store information emerges from the interaction of individual neurons. Moreover, this kind of knowledge might enable us one day to design novel technologies with similar emergent capacities. When it comes to explaining or engineering emergence, one method of choice is to describe the complex system as a dynamical network. In the network picture, the relation between emergent behavior and interacting units translates to the relation between collective dynamics and network structure. In many cases, explaining the collective dynamics of a network requires to consider the global network structure. However, some of the greatest success stories in network science have revealed that already local structural properties, such as the node's degree, may have distinct implications for the global dynamics. Recently, mesoscale properties have come into focus of network science. Current questions are: can considering a mesoscale structure such as a single subgraph already allow conclusions on properties of the network as a whole? Can we extract implications that are independent of the embedding network? And which mesoscale structure should be considered? In our paper, we present an analytical framework which indicates that the answers are yes, yes, and in any case, the symmetric. Our approach uses that both dynamics and structure of a network can be studied in terms of matrix spectra. In case of the dynamics, the relevant matrix is the Jacobian matrix, whose spectrum contains information about the system's long-term behavior. In case of the structure, the relevant matrix is the adjacency matrix, whose spectrum contains information about topological properties of the net. As recently discovered by MacArthur and co-workers, the spectra of adjacency matrices have an interesting property. If a network contains a subgraph that obeys certain symmetries, some eigenvectors of the adjacency matrix will localize on that subgraph in the sense that all entries that correspond to nodes outside the subgraph will vanish. In our paper, we show that in many dynamical networks, localized eigenmodes of the adjacency matrix lead to localized eigenmodes of the Jacobian matrix. As the localized modes are insensitive to the topology outside the subgraph, associated dynamical instabilities will A. occur in any network that contains the symmetric subgraph, and can B. be analyzed without considering the topology of the embedding network. In practice, this means that given a dynamical network model and a number of symmetric topological building blocks, we can calculate the bifurcations induced by each of the building blocks separately, universally valid, and at low computational cost. The results can then be used to approximate or explain the bifurcation diagram of any model realization that contains the symmetric building blocks. In our paper, we illustrate the idea by means of networks of delay-coupled delay oscillators. For a start, consider a small example network that contains only one symmetric building block, the directed triangle. First, we calculate analytically the localized instabilities associated to the building block and plot the results in a two-parameter bifurcation diagram. Next, we calculate numerically the bifurcation diagram of the larger network. The colors in the plot code the number of positive eigenvalues of the full system Jacobian. Changes in color indicate bifurcation lines. The agreement between both plots confirms that the characteristic instabilities induced by the symmetric subgraph indeed explain parts of the global behavior of the full network. Now consider a network with several symmetric building blocks. A network containing a directed triangle, a directed hexagon, and a star-like motif is expected to display the aggregate of their characteristic instabilities. Indeed, comparison with the numerically obtained bifurcation diagram confirms that the characteristic instabilities induced by the different symmetric subgraphs superimpose without interfering. Let me summarize. In biological networks, up to 80% of the nodes belong to symmetric subgraphs. The ability to analyze their dynamical implications will advance our understanding of the role they play in the functioning of the respective complex systems. Reversely, the ability to assemble and combine topological building blocks with defined dynamical implications may facilitate the design of future technical systems that exploit emergence in complex systems.